this is where we were. Nothing great. Did that. Stayed in Canvas. All new. This is all about relations between two variables. We saw that. In several ways, we looked at the general logic behind hypothesis testing, and we did a lot of hypothesis testing. What about two categorical variables? One categorical with two categories and an interval variable, or two interval variables. Then a slight detour to sample size determination on Wednesday, and we will continue now with multiple regression, which is one y that we want to predict, and that y is supposed to be interval scale, and a bunch of predictor variables where the bunch starts at 2 and can in principle be as large as we want to try to predict y. Okay, so let's see. This is what it is. Y should be interval. The thing that you're trying to predict. So we need something there that is not binary or not a set of different categories. All that will come later, but we'll start with the easier case where the thing that you want to predict is something on an interval scale. And luckily the predictor variables can in principle be anything. So a categorical variable with two categories or with four categories or interval or ordinal or what have you, anything goes. As long as you know how to actually do it. And quite a bit of the time we'll go into trying to explain how you do it. For many of these, this will be relatively straightforward. Only the categorical variables will be a bit of a nuisance. There are quite a few wiki data sets online for this module. This is one of them, and we saw this one earlier in one of the other wikis. This is where the target variable here will be the price of wine, of Bordeaux wine in this example actually, and a bunch of predictor variables here. This guy, Orly Aschenfelter, had the idea, well, predicting the price of wine, how complicated can it be? It's a bunch of grapes in a bottle, so what we're trying to do is, well, we would know how much it contained during the October-March period, and what the temperature was in the summer, and how much it rained when we harvest the grapes, and a couple of other things perhaps. Then we should try and come up with a quite decent prediction for the wine price, and actually it turns out to be one of the few models that we will encounter that has a really high R squared compared to the wiki. And this is stuff that you can try in the wiki for yourself. This is the set of predictors that it has, perhaps are one or two other ones. I added here a couple in gray that in fact we do not have, but just to emphasize that in principle you could have any kind of predictor here. These are all interval scale. And this one, the one in red, that would be a categorical one with two predictors, yes or no. Or here the type of the grape, perhaps it's a Pinot Noir, a Syrah, or a Cabernet, totally different categories. That in principle could also be used in the prediction model. In Stata, this is done through these. REG for regress, we saw that before when we had just one predictor X to work with. A command that is I dot and then the variable name behind it. We'll see tab once more and a test command, and that is for today I think all that we need. As you will see if you go through the module that is about multiple regression, and in fact there are several for multiple regression, there you see quite a few more wikis than you are used to, because for this part you need more practice. So you'll find, first of all, that there are screencasts and annotated output by other people who did multiple regression analysis. So you can see how it goes if somebody else does it. Or that you can see how it goes if somebody else explains it, if that works better for you. So that might be helpful. There are more wikis in there, and there's a reason for it. The easiest metaphor that I could come up with was this one over there. If you go to IKEA and you buy 3 Billy book cases, then, for the first one, it will take 2 hours and you will have one of the shelves backwards. And the second one, will take you an hour and now it's okay. The third one, in principle, you can do this with your eyes closed. The metaphor is actually quite decent here because the theory here is not complicated. You have a plug here and there and you have to attach a screw or something else every once in a while. Not complicated. So if you explain to somebody what it is that you need to do, you can do this. Doesn't mean much. But that first one is difficult. It will cost you time and you'll have it backwards. And the second one will be better. And the third one, that is where you do it with your eyes closed, that is where you need to be for these multiple regression examples. And And the only way to get there is simply by practicing. In fact, I feel so strongly about the practicing part, not only about the multiple regression, but also about that other stuff, that there is an assignment online. Not yet, I'll have to click it open, but there will be an assignment online. Simply to retake the test that you did. You can do this as many times as you want. And there is only one aim. You need to score at least 31 out of 36. We had 40 questions in there. I got rid of the 4 ones that were a bit shady. So we're left with 36. Should be relatively easy to do. In the end, finish up with at least 31 out of 36. If you had this already, great. And it should be a walk in the park. If you did not have that, then you can try it again as long as you want. And there is only one aim. You have to, or two actually, you have to complete it in this calendar year. So the deadline for this is December 31st, 2359. And the other thing is you have to score 31 out of 36. And what the quiz will do is remember your highest score. So you need not worry that if you accidentally reach 32 and you want to practice again, that you're going to mess up your score. Okay, I'll put that online after today. Okay, then the actual today part. This is the aim of today. What you should be able to do after today is, first of all, run sequences of multiple regression analyses. That's aim number 1. Including those, and that's the sort of counterintuitive part, where we have categorical variables, and you have to obviously be able to interpret the output. And we have one main data file that I will use as an example, and the data file is called graphic.dta, and I think I have a screenshot of that. Yeah. Here you see part of the spreadsheet in Stata. On the left you see a variable that's called dangerous. What we asked people was, I think, for 7 traffic violations. Did you commit the following traffic violation in the last couple months? Yeah.
Yeah, I was just wondering about the practicing test. If you already passed it, the 31 out of 36, do you still have to make it?
Do it anyhow. Practice it with me. So we have here a couple missing violations as well. Scores of 0, quite a few. The people who say, I didn't commit any of these traffic violations, and the traffic violations that we had were, let's say, relatively innocent. So I parked in a place where actually I knew you shouldn't be, or I drove 120 where 100 was allowed, to make it, let's say, relatively easy to admit to these kind of things. But still quite a few people say that they didn't commit any of these, although there were a couple who admitted to at least 6 of these 7. So that's the thing that we're trying to predict in a minute. Officially, actually, this is not really an interval scale variable. It's nicely defined where it is defined. The difference between 1 and 2, that's 1. It's the same as the difference between 3 and 4, also 1. But the problem here is that this is bounded above and below. It cannot be lower than 0, and it cannot be higher than 6 or 7. So actually, it's not completely interval, but for now, we'll settle for this. And we have some more data here. Let's see. We have if the person who answered the question was female, yes or no. Also age, and a couple more things. We have the number of kilometers per year that somebody drives in a separate column. And we also ask for religion. And all of these we will see in a minute as being used as predictor variables. Okay, so that's what we're aiming for. Let's see. This is the general equation that you will see more often. This is what multiple regression is. We try to predict y as a weighted sum of predictor variables x. So it looks like that. Y equals b0 plus b1 x1. We know that from the simple regression example. The only thing that's different now is that we have more, and that we add these as separate scores, separate predictors that we can use to predict the target variable y. Again, might be 2 reasons to do it. First, I'd like to be able to predict, for instance, tomorrow's weather or the stock market or the price of a bottle of wine. And I basically perhaps do not even care so much if I really understand why it works, as long as it does. Or I might be willing to understand what's going on here in a bit more detail. And then I don't care so much about how well the model fits, but I just want to understand what's going on. Multiple regression analysis is what I will use as the standard term. Ordinary least squares is what you hear quite often as well. Basically all the same thing. Then it's quite a good idea, I think, to emphasize that this is the standard workhorse of statistics. So this is, if you know how to do this, then in principle you can predict lots and lots of things quite good. And many businesses do as well. For instance, banks might try to predict your credit worthiness. How likely is it that you are going to pay back, or how much will you pay back in the end? Or, for instance, the expected number of hamburgers at McDonald's. You might wonder why, when you enter a McDonald's, that there are always a couple of burgers sort of waiting for you. Well, this is because they predict how many customers will end up there, and this is also why, let's say, there's sort of weird choices if you have a sort of a strange preference, different from the rest of the world. In terms of when you show up at McDonald's or what you order, then it is much more likely that they have to prepare it on the spot for you, but most of the stuff is already lying there. This is because they predict this. Let's see, what else we have? This is the value of job candidates. For 25 or so people who we interviewed, and we have to estimate which of these is more appropriate for the job. Multiple regression kind of stuff. This could be multiple regression. One of the examples where we had the experiment with the voltage, the millimeter experiment. Our predictor could be, is there a warning sticker on the machine? We're trying to figure out, does it make a difference if the sticker is there versus if it's not there? How high the voltage is that people will actually give to other people in the experiment. Or a typical experiment that we at ACI would do is we vary lighting conditions, and we try to figure out if people, for instance, feel better depending on the kind of the light that they are being shown. Long list of other examples, don't want to go through all of these, but the basic thing is, well, if you know how to do this, then in principle you can get to work on many of these different examples. Okay, so all this is just sort of an extension of simple regression. So very briefly, because it makes the extension easier, this is what we had. One predictor x, where x over here is interval scale, and the y over there is also interval scale. And we're minimizing these distances. So we minimize this, look at the deviation, that's the observed minus the model, where the model here is a straight line. That thing we minimize, and then we end up with a straight line. Nothing new. And what we're trying to find in this case is, well, the formula for the straight line over there, so we're trying to find the b0 and the b1. Where y is a vector and x is also a vector. And the only thing we're going to do next is increase the number of x's that we have. Okay, let's do that on the traffic data that we have here. And I'm going to focus first on just 3 of the variables. First, that y variable we had already, it was dangerous. Then we have kilometers per year, that's an interval scale variable. We have female, that's a categorical variable with 2 categories. And we'll run a true multiple regression with both of these included, and then see what happens. Okay, so here we go. We want to predict the number of traffic violations. That is what's called dangerous data. The maximum actually could have been 7. I think the maximum in the data is 6. Yeah.
Isn't it already more logical that if you drive more, that you have more violation?
I'll get to that, and because exactly multiple regression is going to help clarify that issue. So first guess would be, okay, forget the kilometers per year for a minute, but let's go for gender. You know, males are reckless morons, so they make many more traffic violations than females, and we're going to see if that is actually the case. So what we do is we come up with one predictor variable. The variable is female. Being female helps, because then you're not male. And we'll see if that indeed works. And if we do it, we would get from this data. I could show you the regression table, but I can simply show you what the line looks like. Dangerous equal to 1.48 minus 0.66 female. Okay, so this is actually supporting that claim. Females score lower on the number of driving violations that they have. On average, they score 0.66 lower on this scale from 0 to 7. So let's see if we have this model here. So same model here on the next slide. There we have it. What would that mean? Well, that would mean that I can predict now what I think on average males and females score. First for males, that's 1.48 minus 0.66 times 1, because if you're a female, you have a 1 for that variable, equal 0.82. And for males, it's the same, but only there now we have a 0, because all males score 0 on this variable, 1.48. Okay, so indeed that 0.66 difference over there, that is exactly what that coefficient there means. And we see that our intuition that males are more reckless drivers here is indeed corroborated. See, a couple of things we need to note here that are perhaps relatively obvious now, but will become more important when we make this a little bit more complicated. First, we see here we have a categorical variable, gender, male and female, and we create dummy variables that are binary scored, 1 or a 0, in such a way that the name, in this case female, already suggests, okay, the female is 1 and male is then 0, so I can see by looking at the variable simply how it is coded. I don't want to code that as 1, 2 or something. And something else, we have 2 categories, but we need only 1 variable. Okay, so there is no need to add a extra dummy variable here, male or something. In fact, that wouldn't even work. So we have 2 categories, and one of them included is enough to get predictions for both categories that we have. That will become more important in a minute. Okay, and then, yeah, obviously, the prediction here is, okay, I predict 0.82 for all females, and I predict 1.48 for all males. That, in all likelihood, will not be a very good model. So our R squared will be low, even though we've learned something now. There is a difference between males and females, but we're not predicting very well just yet. Okay, one more note about the 2 categories, and that we then only need 1 dummy variable and not 2. Well, here's where you see how this would not work. This is what would happen if instead of doing this, which is correct, you would simply include a dummy variable for each and every category that you have. So I include both female and male in the model. Well, then simply we can go through the math here. Male is defined as 1 minus female, can be anything else. So this means that this model over there, with these 2 variables in there, is necessarily the same as that model over here. And this is not identified. Here I can come up with different sets of answers that will give you exactly the same model. For instance, a 1 for B0, B1, and B2 would work, and a 2, 0, 0 would be exactly the same model. So this is actually showing why having 2 of these dummy variables in there is not a good idea. And in fact, Stata protects you a little bit from this, because if you would do this, it would throw out one of these variables. So in that sense, you need not worry too much about it. But you do have to see why you need 1 dummy less than you have categories. Okay, next bit is your question. Now you can, of course, say, well, I have an additional argument here. It's not that males are so reckless. There is something else here. Could very well be males drive much more than females. And if they drive much more, it's reasonable, not more than reasonable, nothing to do with recklessness, that they commit more traffic violations. And one way to do that would be to run the data differently. Split the data in 2 groups, the one who has high mileage and the one who has low mileage, and then run the analysis again. So then if we have a separate group, all these people here have low mileage, so they more or less drive the same amount of kilometers per year. We rerun that regression, and now we test if there's still a difference between males and females. And for the other part, we do that as well. All the people who drive a lot of kilometers, we rerun the regression and we check if there is a difference. There's nothing wrong with that, by the way, but it does have a couple of serious drawbacks. Obvious ones, I guess. Yes?
Where do you draw the line between high mileage and low mileage?
That's one. So you could argue, even if I draw a line, let's say halfway, then still I might have people who are, only drive around the block versus 10,000 kilometers per year, which is still quite serious difference, you could argue. So that's not clear where we draw the line exactly. What else?
You might have very little females with high mileage.
Yeah, that might happen too. So if we at some point draw the line somewhere, it might occur that, for instance, in a really high mileage range, there are no females there, so we cannot even compare males and females anymore. What else?
I think if you're doing research, then people can say, yeah, you chose the mileage so that we get results.
Yeah, so in a way the same argument as mentioned before. You have to think about where you draw the line, and then you have to convince the rest of the world that that is reasonable and that the result will not depend on that you draw here and not there. Indeed. What else might go wrong? Yeah.
You might need larger sample groups.
Yeah, why?
Because if you draw a line somewhere, it could be that low mileage is 90% of your test and the other one is 10%. So you have very little points, which is very sensitive to outliers.
Yeah, that could happen, so that if you draw the line somewhere that now I have 10% over here and 90% over there, then of course you could argue, okay, then let's draw the line somewhere else. Let's draw it here a little bit so that we have 50-50. What else? Because there is more that might hurt.
Yeah, the interaction between miles driven and the gender is not displayed.
Yeah, sort of, I think. What do you mean by the interaction?
Yeah, so it's not necessarily that high mileage are specifically males. So yeah.
Okay. I don't want to go there at this point. We'll get to interactions a couple lectures down the road. But there are more, let's say, things that are not so nice when you do this, besides the ones that we already covered here. Nobody else? You don't have any ideas left? Yeah.
Making an interval variable categorical, so you throw away lots of data.
Where am I throwing away data?
You're not using the difference in the low mileage things.
Oh, yeah. Okay, yeah, sure. So you could argue then at this point here, well, this is a sort of, at least not very efficient, because we started out perhaps with, 1,000. I don't know exactly how large the data set is. And now we have 500. And in these 500, it's less easy to find something that is statistically significant, simply because you have a smaller sample. And we could, try to make this really more serious. Let's say that we start with 1,000 people in our data set, and we got a line here through halfway. So we now have 500 here and 500 there. There are quite a few other variables that I can come up with, besides kilometers per year, that might also have an effect here. So if this is the standard thing to do, we could argue, okay, now we have 500 here, low mileage, 500 there, high mileage. What is the next thing to do? I come up with something else, some other variable that may have an effect here. Whether you like driving or not, or some other measure that we have. Now I'm going to split up again. I have these 500, and 2 of 250. And these also in 2 of 250. Now I have 4 of 250. Now, first of all, my power goes down, so the probability that I find something, even if it's there, will become lower, because my sample on which I'm going to calculate is becoming smaller and smaller. If I do this for 8 variables, I have really, really small samples left, basically nothing to work on. And even if I have, let's say, 4 of these, I might now find, for instance, yes, there is a difference, no, there is no difference, yes, there is, no, yes. So then it's not obvious anymore exactly what I want to conclude here about the whole sample. So this is working if you don't have too many of these, and you can, let's say, quite appropriately draw a line somewhere and then end up with 2 relatively homogeneous groups, then it might work. But it doesn't help in the sense that if you have more than these, more arguments, more predictor variables, then you run out of data pretty fast. And you have to repeat all your analysis a gazillion times for each and every one of these small subsamples you have created. This is also why this second solution, multiple regression, is strong in that sense, because the only thing you need to do in fact here is add that variable as an extra predictor variable to the model, and then sort of by miracle, you could argue, you get exactly what we want, because these that you had before, these worthy coefficients that are being estimated by Stata or any kind of other model, mentioning, okay, for the difference between males and females, that difference here is B1. And here, for the number of kilometers per year, for every extra kilometer per year that you drive, you get B2 extra in terms of that danger variable. Now what you get if you do this together is, also if you have more than 2 variables here, for each and every variable you get the net effect given that you have included all the other variables. So this is controlling for that there are differences in terms of kilometers per year, and then checking is there still an effect of being male, yes or no. So let's see how that would work out. Here I did this the analysis in Stata twice. Let's see if you can try to Wait, that was not the right button. Can I change this? Okay, that doesn't help much. There we go. So here, the same thing that we had before. That's the line that we estimated when we only have male or female. 1.48 minus 0.66 times female. So the effect here, the difference between males and females is 0.66. Same thing here, the only thing that I added here is an extra predictor variable, kilometers per year. And what we see now is, well, a couple things. First, that the female variable coefficient here is now smaller, or closer to 0 than it was. So the effect, the difference between males and females, which was 0.66, is now closer to nothing, but not completely. So part of that 0.66 effect is explained away by the fact that we control for the number of kilometers per year. And that number of kilometers per year has a very small coefficient, but you can see that now. So what you do see here is these are all highly significant. So we do find here that there is indeed an effect of kilometers per year on the number of traffic violations that we make. It seems like the effect in itself is really, really small, 0.000, and then you get a couple numbers. But the number of kilometers per year is measured in actual kilometers. So for every extra kilometer that you drive in a year, which is not a lot, you get this extra coefficient on the dangerous variable. But in fact, it's perhaps easier to think about for an extra 10,000 kilometers per year. And then let's see if we get the decimal point. 1, 2, 3, 4, this 0.2, let's say. So for every 10,000 kilometers per year extra, you get 0.2 extra on the dangerous scale. So the size of the coefficient here shouldn't fool you into thinking that this is nothing. This is simply because the kilometers per year variable is very quite a lot. Okay, so what we see here is we had an effect of male versus female. The effect was 0.66. If we control for kilometers per year, it gets less. So in part, that male-female difference is explained away by the number of kilometers per year, but there still is an effect that's still there. Yeah.
Yeah, I was thinking if you copy the kilometers per year variable into a 10,000 kilometers per year variable and you run tests again, would it also influence the coefficient it has on female?
No. So you could do this, and what would happen is you get exactly the same model. The only thing is that the kilometers per year coefficient is now more easy to interpret, 0.19. So there is in fact a reasonable argument to be made to create a variable like this, define it as 10,000 kilometers per year, and then you get something that is more easy to interpret. It would do nothing with anything else that's in the model. Would also be weird, you know, that it would be strange if you divide everything by 1,000 and then your model fits better. So that's certainly not going to happen. Any other questions about this? Yeah?
Does the R squared value also say a lot about that this is a better model?
Well, yeah, say a lot. Of course, here what we're trying to aim for is understanding why there is a difference between males and females. So we're not hoping here that we have a really good model, and in fact we don't. 0.06, which is close to nothing. And it's also not so weird because you're predicting only by using two numbers. And here it gets a little bit better because the kilometer per year variable, first of all, has more detail in it. It's an interval scale variable, and it gives us an extra, well, let's say an extra 0.04. And in principle, I would say that, yeah, you know, it says that this is getting better than it was here, but I could have seen that basically also from the fact that this one here is significant. So I wouldn't mind so much here about what the R squared actually is. Anything else? Because what you could do, yeah.
Is there also a way to, how we predict that the mileage per year also, or kilometers per year also influence other more variables in the data? Is there also a way to test which of the values will use
The number one point here is multiple regression allows inclusion of more than just one variable. Here I added one, but if we have 20 others in the data, as long as we have data points enough, we can simply add them to the model. No problem. And what sort of works for you in a way that what in the end you see for all these, let's say that you have 20 variables, I think we actually do in the data, you include all of them. I have to check how many cases we actually have, or 720, so we can get away with quite a few variables there. And you can see what all the net effects are of these separate predictor variables, where net effects means the effect of that variable, given that I have the other 19 in there. That will work. And we do that, in fact, as soon as we get rid of this. Okay, so the other thing to get from this, besides that you can make this list way longer, is that you can get some of the information of what's going on from running subsequent analyses. So the fact that I here see, yes, kilometers per year explains away a little bit of the difference between males and females. And for that to be included, I need two regressions, one here and one there, so that I see that the effect that was there in the beginning is now diminishing as I keep adding variables. Okay, yeah.
How can we see if it's significant or not?
What is significant?
The numbers that we got.
Yeah, I'll go through one of these and then go through all the columns that we have a couple slides number. So we'll get there. Okay, let's see. Yeah, this you'll see quite often, I think, as the standard multiple regression equation. Or actually, what we should do, but often forget, is add something over here, epsilon for the residual, because that's the actual model that we need, and we need some statistics in a minute. Thus far, we didn't do any statistics, right? We only tried to fit a line through a cloud of dots. There's no normality, no probability, no nothing involved there, but in the end, we do need this. Multiple regression is so standard, if you have statistical software, it doesn't matter what it is, it can run multiple regression. This is old, it's easy to implement, it's a closed form solution, so there's no complicated optimization going on behind the scenes. You can do this in any kind of package. We'll use Stata, but just to show you that we do not use that because the multiple regression is so weird, but it's simply one of the standard things that's in there all the time. You could wonder, however, linear, isn't that a bit simplistic for all these to have a separate effect on y? Couldn't there be all kinds of weird interactions going on that if the number of kilometers per year is larger than 20,000 and you're not religious, then all of these kind of things might happen. But very often for data sets like the kind that we are typically collecting, we very regularly have ideas of the kind, well, we think that if this variable increases, then the target variable will increase as well, or will decrease, and nothing more specific than that. So this is not physics where you could have, let's say, a really complicated equation that we also know or is supposed to hold, and then we can test it. None of that is necessary most of the time. And in fact, even if you would have it, then let's say a first-order Taylor expansion, if you happen to know what that is, would be linear and would give us a linear approximation of the thing that we're after. So very often this is actually good enough, and we do not need any complicated stuff. And the second argument here that we need is that it has to be linear in the variables themselves. So we can easily do something like this, where we include the number of kilometers per year squared, or the square root of that variable, or some other kind of transformation. As long as we keep this separate, then still this can be estimated. So here we are trying to estimate the best fitting parabola of kilometers per year as a predictor for dangers. That can actually work. The only thing that cannot work in multiple regression is something that looks like this, where we cannot separate all these different things, although if you look at the first order Taylor expansion of this, it would also be nicely linear. So this cannot be done with multiple linear regression, and in fact it can be done with something that's called nonlinear regression, so it's not that statistics is out the window here, it's just that you need a different kind of procedure. Okay, so one final bit on why this is so beautiful, and why it takes me 3 of these lectures to make sure that we all get it. Well, one is this thing that we already looked at. we can account for all kinds of intervening factors. So you could think, when we see an effect of, yeah, there is a difference between males and females, yeah, but this could be because of this, because of that, because of this, because of that. Well, if you have all of these measured, you can simply include them and control for it. So then all arguments of the kind, well, but in kilometers per year, very important here, that is simply explained away. We included that, we controlled for it, and we shouldn't bother about that anymore. Second thing is, as soon as you know what multiple regression is, you should be able to see that quite a few of the things that we did before, and that we will do, are actually special cases of multiple regression. One would be a t-test, I'll show that in a minute, so that, two groups, and we have an interval scale variable that we want to compare. We did that already. You could also do this with multiple regression, and would give you exactly the same results. We'll look at ANOVA, or analysis of variance, when we compare between more than two groups. There are separate commands to do this. In fact, you could also do it with multiple regression. It's exactly the same. So not almost, but really exactly the same. Correlation, we had that before, and there you already saw that this is actually the same, or can be achieved also by standard simple regression, 1y, 1x. As soon as you know how that works, you know how quite a few of the other ones work, and even the stuff that we won't treat here, but it is, let's say, slightly more complicated, is sort of multiple regression with a twist. Okay, so you want to predict, let's say, a target variable y that's not interval, but that is binary, could happen, then it's called logistic regression, and that is just multiple regression, well, slightly different. So as soon as you understand this, you're good to go also for the more complicated stuff. Let me show you how the t-test works. T-test is a special case of multiple regression. There, I'm regressing dangerous on female, and I got that minus 0.66 and 1.48 again. I could have done that as well using a t-test, as long as I abstract away here from the stuff that we need to test, so normality for both groups and stuff like that. If I would type here t-test dangerous by female, then you'll see, I think I have that, yeah. First of all, that minus 0.6641665, that you exactly see that here too, the difference between the two means, and also that the significance test, there the test value that we have here is 6.68, is exactly the 6.68 that we have over there, and given that these numbers are the same, we also have that the significance values are the same. It's here not so easy to see because they are so small, but this 0.0000 is the same one as over there. Do note, by the way, that to get the equivalence, the unequal has to be left out, because if you do unequal, then the significance values are calculated slightly differently, but in any case, they are the same, and you can calculate them in both ways. Okay, let's see. One more thing to show in terms of notation. These hats above the coefficients, this usually denotes predicted values. So the B0s is when we do not know them yet. When we have estimated them using data, then we call them B0 hat, B1 hat, and so on. And if I actually calculate a prediction for each and every case of my data, that will give me a predicted y hat. And these hats are typically for prediction purposes. Again, we have a measure of deviance that's nothing nothing different, I should say, from the simple regression case. We look at the actual y minus the predicted y. We square that difference, and we sum it, and that is being minimized behind the scenes. So we have again these sum of squared residuals as we had it before in standard regression. We have that here too. If you are, let's say, a visual learner, you can think about this, where we have an interval x here, then we have a line through a cloud of dots, but then on a piece of paper. If you have two of these predictor variables x, each and every one of them also interval scale, then we have this, a cloud of dots in 3D. We're trying to fit a plane through that cloud of dots that fits best. Obviously, if you have more than two x's, it starts to be complicated to visualize. We're not so good at more than 3 dimensions, but in principle, the same thing is happening there. We're trying to fit a cloud of dots as good as we can using the predictor variables that we have. Okay, then a little bit about model fit. In a regression table, that is that the part at the top, where we see these sums of squares and these adjusted R-squareds and so on. Luckily, how well the model fits is totally the same, actually, as it was in simple regression. We've got one y and one predictor x. We knew how to do this. And here it's the same thing. We start with a very poor model, just including the mean. So we predict the target variable y just by guessing the mean of y. That's not a very good model. Gives us a total sum of squares over there. And what we do is compare this to how far off we are when we include all the predictor variables that we did. That could be 1, that could be 2, that could be 20, doesn't matter. But if we get the new model in there, we predict our target variable based on these predictors, and now we hopefully get closer to the actual target value. The sum of the square residuals is now smaller, and this value here is what is called R squared. So this is nothing new, only for simple regression we have 1x in the full model here. Now we may have 12. Or also something that was similar in the simple regression case, you could also look at the actual y that we have and the predicted y that we have. In the simple regression we had a predicted y based on 1x. Here we may have a predicted y based on 12x's. Still, idea is the same. The correlation between these two and then squared is called R squared, and that is a measure for how well the model fits. So that, in a way, is nothing new. The only extra thing that we get here is that we somehow want to be able to control or compare different R squared values across different analyses. So if you get an R squared of, let's say, 0.45, and I get 0.1, we like to be able to say that your model fits a little bit better than mine. But to have that, we need to have sort of a fair comparison. And for that, we need something that's called adjusted R squared, which is also the output in a minute. What the the adjusted R squared does is try to control for a couple things. First, for the number of predictors that you have. Obviously, if you have more predictors, then in all likelihood you will predict better. You know, there will be variables in there that help you. Some of them may not, but that doesn't hurt. And the ones that help you bring you closer to your actual y. So that will be sort of an unfair advantage. If you have 100 variables to predict, then I have 3. And we need to take that into account. And we do that, you see that, where is it? P over there, it's the number of predictor variables that was used. So the formula that is being used here is sort of giving a penalty the more predictor variables you have actually used here. And also gives you a penalty for having not a lot of cases. If you only have a handful of cases, the probability that you get something by accident is larger. Or if you get something that's not really there, actually, is larger, and there's also a penalty for that. So if you look at the formula here, you see that the adjusted R squared is actually the original R squared minus what? Well, a little bit is subtracted from that R squared. This thing is necessarily positive. This is also necessarily positive because that and the number of cases is really way larger than the number of predictors. So you subtract something from the original R squared to take into account that you shouldn't have too few cases and that you also shouldn't have too many variables to predict with. Okay, let's see how that goes. Here we see it in an actual table. There we have again the regression of dangerous predicted by female and the number of kilometers per year. The R squared is 0.0898, and if I fill out the formula with the numbers that we have here, you see that the adjusted R squared, which in this case is very close to the thing itself, 0.0872, can actually be calculated also by hand if you wanted to, based on the numbers that you see in the table. So it's a convenience that you see that adjusted R squared. Okay, now, up to now, there was no statistics in there. No probabilities, no distributions, no nothing. And we need to have it in there because we want to say something not about the sample, that's easy. You know, the plane that would fit the cloud of dots best, calculating that needs no assumptions about probability, but we need some statistics here. And let's see what we need. Well, first we have that there is in all likelihood, a bit of difference in the estimated coefficients that we have in the sample and the actual coefficients in the population. And we have to somehow account for that. There are different ways in which this can go wrong. We might have a measurement error, so the thing that we measure is not exactly measured completely right. I'm measuring your IQ, for instance, on a given day, but maybe you had a bit of a bad day, or just the test was slightly more difficult than it used to be, or you made some error somewhere. So I have measurement error on the things that I am trying to measure here. I also have sampling error. I'm taking a sample from the population. I might get a bit of an unlucky sample or a very lucky sample. So what I get might not be completely representative of what the actual population is, and there might be all kinds of other junk in there that we do not know of. So these are the typical three kinds of error stuff that you could have in there. So how can we say something about these BI values that we're trying to estimate in the population? Well, by imposing a couple of assumptions. And the assumptions that we need here are of the following kind. This is actually the full model that's being used in multiple regression. So this far we did this already without checking that this was actually okay, but this is what we need. First of all, this is the main model where we have that epsilon at the end. That epsilon is called a residual, and we assume something about all these epsilons, namely that they come from a normal distribution with a mean of 0 and a fixed variance, in this case called sigma squared. Okay, let's first look at that normal. Well, so what we hope is that if we would look at the residuals here, that they have a shape like that. That's relatively easy to do. And also what we are assuming here is that the variance of these residuals, the residuals is how much you miss the actual value that you want to predict, that this variance is fixed. So something that is not allowed to happen is that for some cases you predict quite well, so the residuals are relatively small, and for a part of your data you predict very poorly and your residuals are quite far off. Here you have high variance, here you have low variance. That's not allowed. And later on we will be able to actually check for this using a command that we will run after the actual regression. But for now you have to know that this is the actual assumption that we need, otherwise all the statistical stuff makes no sense anymore. And something else that needs to be the case is that epsilon itself shouldn't depend on any of the predictor variables x. So it shouldn't be the case that for a given x there is a relation between x and the residual. For instance, that if, let's say, age is increasing, if I predict with age, that for small h I have small residuals, and for large h I have large residuals. Also something that's not allowed to happen. And that implies that even though we are running these regressions now as if nothing is being assumed here, actually you need to be able to test this, and the only way to test it is after the fact. So we do it first, and then we check whether or not what we already did was actually allowed. Okay, this is just a warning for what we're up to later. First, we're still continuing with how to actually test all this. Okay, so this is the official model. Okay, then, well, what we have here is we can come up with a model like that with estimated B0, B1, B2, and so on. And what we're testing is all the time in H0, the coefficient in the population equals 0. So for instance, the B1 over there, we've estimated that, and we are comparing that coefficient with 0. How likely would it be that we get the data that we have if indeed in the population that B1 would be 0? The statistics programs obviously give you, and we've seen that a couple times, these estimated B's, and you get what's called a T value, a P value, and a confidence interval. I'll show you that in detail in a minute. So in this sense, when we went through the standard setup for hypothesis testing, this is nothing new. Okay, so I have a H0 again. That H0 is being tested by some test statistic that we don't bother too much about, but the value of the test statistic says something about how likely it is that we would get the data if H0 would be true. Okay, so let's see how that goes. Here we have a regression, relatively simple one with only female as a predictor. We saw that one a couple times before. So let's see what we have here. First column, coefficients. So these are the estimated B's, B0 hat and B1 hat in that column. Then there we have these sums of squares. When I said something about, okay, we first look at the mean of y, how good a predictor that is, and then we look at the actual model, how good a predictor that is, and then we compare all these sums of squares, and all that is in this table over here. Here we see the actual statistical tests where the H0 is the coefficient equals 0, and here you see in both cases normally. What else do we have? There we see a little bit of, let's say, other stuff related to the statistical tests. First, that we have 0.000 here has to do with the fact that we have a test statistic over there, in this case called T, that in these cases is quite far away from the standard minus 1.96 and plus 1.96. That's the standard area where hypotheses are actually supported. So here you see this one is really smaller than minus 1.96, so far away to your left, which causes that this thing is highly significant. Here it's even stronger, 21.17, all the way to the right, way bigger than 1.96, so this is a totally statistically significant value over there. And let's see, what else we have? There, the 95% confidence interval. From the 95% confidence interval, you can also see already whether or not H0 will be supported. The only thing you have to look at is 0 in that interval. If it is, then H0 is supported. If it's not, then H0 is rejected. Here, 0 is not in here, so rejected. Here, 0 is in there, so rejected. And this one I will leave for a minute. What else do we have? Yeah, and then of course the regression table, where we basically use the stuff that's over there, these sums and squares, to calculate first, well, yeah, okay, the number of observations, that is only testing how many cases in the data, yeah.
Where you say 196 coming from?
That 196, if you remember that normal distribution, where the mean is 0 and the standard deviation is 1, then if you go to your left and look at the 2.5% cases that are, let's say, on the far to the left, and the 2.5% far to the right, this happens here at minus 1.96 and there at plus 1.96. And that's where they are. Okay, first number of cases that you've used, then that R squared is over there, and the adjusted R squared is over there, and the other ones I'll leave to a future lecture. Well, I can briefly mention that F-test over here, what we're testing here is if the model as a whole is better than nothing. And typically, if you have something like here, the model as a whole, this is only one variable here, so it's not so much. So in this case, indeed, what we find here is that the model is better than nothing, and most of the time it actually will. Okay, if we have this, then what we can do is ask Stata to run different kinds of tests. If you don't want to test with the 0, but with something else, then you have to ask, and Stata will deliver. So let's see. If you have a different H0 that you want to test, for instance, well, let's see. Is it here the case that is minus 0.66? If we test with an H0 of minus 0.5, could it be the case that the actual coefficient is minus 0.5, and that we then get data like this? Well, now you see that's actually supported with this test over here. And I could put any value that I would want over there, asking Stata to come up with a different number. Let's see, and yeah. What you could also do is for different kinds of variables, well, in this case, it's a totally clear example, I don't really know why I came up with this, but what you could test here is the coefficient that we have over there the same in the population as the one over here? I really do not see any reason why in this case I would want to do this. I'll show you an example in a minute where it's much more logical, but I could do it, so I could ask Stata to run this test, and in this case, this is clearly not supported. It's totally rejected. This number is a totally different one than that one, apparently, in the population, loosely speaking. Okay, now our confidence intervals, and this brings us to the column that I left out at this point. Let's see, that's the one over here. In principle, this is just an extra because we could try to figure that out by ourselves, because that confidence interval is created in the following way, that minus 0.5 that we see over there, if you would do the following, minus 0.5 minus 1.96 times that number over there, that gives you this left boundary, and minus 0.5 plus 1.96 times the thing it gives you the right value. So this is an extra way to see what you could in fact deduce on your own. So if you would have the standard error, you could create the 95% confidence interval on your own if you wanted to, but Stata gives it to you already. And once again, that 1.96 is coming from the normal distribution. Okay, so this is what a regression table gives you back. And student principle allow you to read what's in these tables and understand what's going on. The interpretation is always the same. What is the coefficient here? Well, this is suggesting kilometers per year. It increases with 1. Then our target variable, on average, is supposed to raise with 0.0000196. Same for female. If you're a female, then, and controlling for all these other things, then the score on the danger variable is on average half a point lower. Any questions about this far? Okay, then over to the part that is usually the most, not necessarily complicated, but at least for some complicated to get. We want to include different kinds of variables, and we're going to have a bit of a ball with the categorical variables, because they are sort of a nuisance and difficult to interpret. Okay, we can have anything there. So interval, we will not look at ordinal for now, but interval and categorical are the only ones that we're going to distinguish here. So let's see what we have in our data. We have in our data religion. I must admit that I do not really have an argument why I would think that you commit more or less traffic violations based on your religion, but you know, nevertheless, let's give it a try. In the data we have here 9 categories. Let's see, we have, sorry, this is in Dutch, we have I'm not religious, I'm Roman Catholic, Protestant, other Christian beliefs, Islamic, Hindu, Buddhist, Jew, or other religions. I'm not sure what that would be, but there you see, well, that for the example here, it's not so convenient to have 9 categories. So the first thing that I'm doing here is I'm bringing this back to 5, just to make it a bit more convenient to work with. And what I'll do here is get rid of the ones that have the least. So what I'll do is a recode this command up here. For religion, all the 1s stay 1s, all the 2s stay 2s, all the 3s stay 3s, and the 4s stay 4s as well. The 5, 6, 7, 8, and 9 I recode to a 5. So all the ones Islamic, Hindus, Buddhists, Jews, and other are now plunked together, with my apologies for any religion who feels bad about being too close to these other ones, but just to make the group a little bit larger. And that generates, in this case, where it's called religion L5. That is the new variable that I want to work with here. And then it looks like this. This variable has 5 categories with, let's say, a decent number of persons in each and every category. And what I also did is I create a variable label like this, label var L5, in which I already mentioned what the 1, 2, 3, 4, and 5 actually mean. That makes it easy, because then if I ask for a tab, then I do get this label in there, and I do not need to check anymore what is what. Okay, now, what are we going to do? If I have something like this, where in this example I have 5 categories in the variable, what I do is I create 5 dummy variables, 1 for each religion that I have, where dummy variables are defined in the following way. I create a variable that's called religion 1, that's equal to 1 if that religion type is number 1, and otherwise it is a 0. So perhaps, let's say a little bit more convenient in terms of the label would be, I have to check what was the first one again, none. So I could also create a variable here that's called none. None is 1 if religion is 1, and 0 otherwise. I do that for all 5 categories. So now I have 5 dummies, 1 for each of the different categories, and I now add 4 binary predictors to the regression equation, not 5. 1 less than I have categories. And for the same reason, in fact, as I used for the male-female example, there we have 2 categories, we include 1 dummy. 1 dummy for 1 of the separate categories, in that case it was female, and the other one is then automatic, because that's the only category that we have left. It's the same here. For 5 categories, as soon as we have 4 defined, then we know that the other one is already in there. And we will see that gives some trouble in terms of interpretation, where the interpretation of the coefficients was relatively easy for interval variables. It's a little bit different for the other ones. Now first let's see how to do it in Stata. There are different ways to do it. These are only a couple, there are more actually. This would work. I do a tab and then I ask for generate R. Now I get 5 variables, R1, R2, R3, R4, and R5 in my data, if I do that. That second, or that thing I could do as well by typing separate commands here. R1 equal to, and then a logical statement. The religion variable equal to 1. Whenever this is true, you get a 1. Whenever this is not true, you get a 0. So this one and that one deliver me exactly the same thing. Or if you are into for loops, at some point somebody asked that can we loop around something here? Well, that will work too, because this set of statements you could also write like this. For values I equal to 1 to 5, curly brace to the left has to be there, not on a new line, and then a curly brace right has to be there all the way after all the commands that you have. And then you can type all the commands that you want to run for different values of I, and the only thing you have to take into account is this over here. And this is not a typo. The thing on the left of the I is a single quote left. On my keyboard, that's in the top left. And the one on the right here is a single quote right, so really another quote. And that is simply putting in the number I. So first run through the for loop, this will be a 1, and there will be a 1, and you get that command, and you do each and every one of them in the same way as you had above. Or there's still a other way to do it, and it is typing the command xi and I dot really L5. Okay, will also work. Okay, anyhow, here we see this happening. First, this is where I actually do this and leave out. Now, I created these R1 through R5, I leave out R1. You can leave out another one as well. I'll show you what happens when you do that. But first, let me just include these and have a look here. Also note, by the way, that what I did here, the variable is called dangerous. I typed danger and not dangerous. That'll work as long as there is only one variable in the data that starts with these 4 letters. Then Stata will understand, apparently that's the one you're aiming for. Female as well, if there is another variable in the data that starts with FEN, then this is not going to work and Stata will complain. But in this case, we're fine. Let's see, what did I want there? Yeah, have to tweak a little bit. What would happen if you didn't know that in this case you need to include 4 instead of 5? So if you just put in 5, then Stata will complain. Note, R3 omitted because of collinearity. So Stata throws one out. I'm not exactly sure what the rule is that Stata uses on which one to throw out. You could throw out any one. In this case, Stata chose to throw out number 3. But in any case, you'll see something like this. And the thing to remember is, first, you have to see this, you have to take this into account and know what it means. This in all likelihood means that you have included one dummy too many. And in principle, it doesn't hurt, as long as you are okay with the fact that this is there and that you have now nothing here and know how to interpret all this. The results are not wrong, but it could very well be that you didn't mean the R3 to be left out, and instead was the R1 left out. And the only way to do that is then by hand. Let's see. Yeah, okay. One thing that I haven't in the slides here, but that I should mention, is that you can do this wrong. In another way, if you simply forget about the fact that this is categorical, then you could, instead of these R1 through R5, you could simply include that rally L5 variable, which is coded 1, 2, 3, 4, 5 as well. So Stata won't complain and will actually give you back results as if that rally L5 variable is interval scale. That doesn't make any sense. It's not possible to interpret it anymore. If I increase 1 in terms of religion, or whatever that would mean a change from, let's say, not religious to Christian or something, then I do get an effect on my nonsense. But the thing is that you have to take into account that you don't do this, because Stata doesn't know how you want this interpreted, and you'll get back a result as if that variable is interval scale. And that simply makes no sense at all. Okay, so let's see once more. This is the part of the output where you only see coefficients here. Basically, what all these models do is, well, they say, if you tell me what female is, what kilometers per year is, what R2 3, 4, and 5 is, then I will give you back a prediction. Yes?
Yeah, if you, in the previous slide that they listed R3 0, how do you know that which of the values you are thinking about if you want to do it manually? You
Yeah.
test them at all of them?
No, I'll go through that in detail in a minute. So that's why I only said leave out one, and in the example I started with R1, and we'll see if it makes a difference at all. Okay, so for any case of the data now, we could actually predict what will be going on. And the thing that we need to consider now is, well, how do we interpret these kinds of values? The first one we knew already, okay, for females, on average, given all these, that we can prove all these, the value is half larger. For kilometers per year, an extra kilometer per year gives me a little bit extra, but now these are 2, 3, 4, and 5s. Okay, there, these dummies are slightly different. Let's see. What do these deliver? It's actually slightly different from the female case as well. So for R1, what do we have? Well, if we predict, let's say for males who drive 10,000 kilometers per year, we could come up with any other example, what do we have? Well, 1.09 is the constant over there, plus 0 times the minus 0.5, 0 because we are looking at males here, not the females, so this coefficient doesn't enter the equation, plus 0.196, that is 10,000 times this coefficient, plus, and then what? 0, because all of these for the R1 group are 0, right? If I'm in category 1, R2 is 0, R3 is 0, R4 is 0, R5 is also 0. So none of these coefficients enter the equation. So my prediction in this case is exactly this number. I didn't calculate the actual number, but this is how I would calculate it. Same thing for each and every one of the other categories. So for R2 I could do the same thing, and everything would be the same actually, all the way up to there. And the only thing that would be added now is minus 0.0778, that number over there. So for R2, I'm in the second category, now I have a 1 over there, and I need this coefficient, and need to subtract that. Same for R3, 4, and 5. I can get predictions here for each and every category that you want me to deliver. Any questions about this, and how this works? Yeah.
How would it work when you leave out another one instead of R1?
We'll get to that in a minute, but just, this is fine, these predictions tend to work, okay. Then, okay, let's see. How do we interpret these numbers? Well, the only way to interpret them is not by saying, okay, here we see that R3 has an effect of minus 0.19 on Y. That's not the way to interpret this. And you can see it from the numbers over here. For instance, let's stick to the R2, this is the first one. The minus 0.0778, that's exactly the difference between R1 and R2. Okay, so that number over there says something about the extent to which R2 differs from the category R1. Same for that number. This number says something about how R3 there differs from R1. And that goes for all the coefficients. So the coefficients for a categorical variable that we have split up in this case, 4 different dummies. All these different dummy coefficients say something about how the actual categories that we have over here compare to the one that we left out. Okay, so this is why it makes a difference which one you exclude for the interpretation of these coefficients. In this case, we're comparing this with R1, which is left out. If you would have left out R3, we get all the coefficients that resemble, okay, compared to R3. Okay, for here, that I think works, and I think I have an example here. Yeah, exactly about this. So let's see. Now we do this twice, once with R1 left out and once with R2. Now let's see what happens. First, we see that everything that is about the fit of the model doesn't change. Okay, so in terms of how well your model is doing, it doesn't matter if you leave out 1, 2, 3, 4, or 5. It's all the same. Also, it would be weird if that would be the case. The data didn't change at all. The other thing is, if you look at the coefficients, not of the separate categories that we're talking about now, but of the other variables, so the female and kilometers per year, also no difference. Okay, so category that you leave out. For all the other variables, there is no effect whatsoever. However, there you do see differences. You see that R2 is only in the top table anyhow, but R3, for instance, is minus 0.19 in the top table and minus 0.11 in the one on the bottom. And this I have a bit bigger here as well. So here you see, in fact, that even though all these numbers here are different from the ones over there, that these results are, let's say, internally consistent and basically give you the same model, even though all these numbers are different. Okay, so we have the difference between R2 and R1. That is that number over there, minus 0.078. That is what you see over there. And we have the difference between R3 and R2. That is this number over there, minus 0.11. That totally consistent with each other. For instance, here R4 and R3, the difference is, well, minus 0.19 versus 0.20, which is in total 0.3896, calculated based on these numbers. Or I could calculate this on the right side. R4 and R3, well, here minus 0.11 versus 0.28. So that difference is also 0.3896. Okay, so what happens if I use, to answer your question, another category that I leave out, basically nothing much. For most of the variables, it doesn't make a difference. For the dummy variables themselves, it does make a difference, but the interpretation of the model and the model, in fact, itself is exactly the same. Yeah.
What's the last category?
The constant. So the when we had just one predictor variable x and one target variable y that we want to predict, we're trying to fit a straight line. That straight line has an intercept somewhere where it crosses the y-axis, and that is at called b0. In the output of data, it's called underscore constant. You may have missed out in the earlier ones because I didn't focus on that so much, but that thing is in there each and every time, irrespective of categorical variables or what have you. Questions about this? All right, so does it make a difference? Answer, well, no. It's exactly the same model being estimated, but you do see some different values, and the different values you only see as coefficients of these separate dummy variables. All the other ones do not change at all, and for the comparisons that you want to make, you simply have to decide for yourself with which of these categories you want to compare. Yeah?
Does it also mean that if you do put every variable in there, if
Every variable, what do you mean?
no, every dummy variable?
Yeah.
If you do put all of them in there, and we saw that the R3 was 0, is it then because the coefficients of the other R's differ if you leave the R3 out, or are they
No. So here, see, where do we have that? So the question was, here is data omitted itself R3, and now says that puts a 0 in there. Is it any different from leaving out R3 by yourself? And the answer is no, it's exactly the same. In fact, if you leave it out, you sort of assume that the coefficient is 0. Because here,
then why would you manually leave one out? The one different also.
well, it depends on where you want your significance testing. So the question is, why would you leave out R1, 2, 3, 4, or 5? Well, if you want to test for, let's say, is there an effect of religion of a different kind, I would like to leave out R1 here. R1 was, I'm not religious, and all the other ones do represent some kind of religion. So I could try to find out if there is a difference for R2, no, R3, R4, and R5. And the no is based on, see, there, all of these numbers over there, above 0.05, so religion doesn't seem to have an effect here. So that would be an argument why, in this case, I would leave R1 out, I think. If you wanted to see other kinds of statistical tests here, you could leave another one. For instance, here, if I would be interested, after running this, in the difference between R3 and R4, in the statistical test of that difference, I can't see it here. And the only thing I can do is, I rerun the whole thing again. Now I leave out R3, and then the coefficient of R4 will give me a statistical test of the difference between 3 and 4. Okay, let's see. Yeah, a couple of side notes here that are good to have. This is what I already showed you a couple times. This is still another way to do it. There is a stata command or stata tweak, so to speak. If you put an I dot in front of a variable, as we did over there, then what you get is output that looks like this. You tell stata by the I dot in front of this that, okay, what I want is separate dummies for each and every one of this variable. And if you're not interested in the dummies themselves, you don't want to use them later on in your analysis, it might be good enough. The only disadvantage is, again, here stata will choose the reference category for you. So here 1 is left out, obviously. 2, 3, 4, and 5 are still in. But if you do not mind about that and simply want to check what happens if you include this variable, then this could work as well. Let's see. Yeah, so the difference is for the thing on the top there, you have to do it manually yourself. Tab, religion, comma, generate R, and then you get these different R's. And at the bottom you don't have to, but then you also do not get the dummy variables in your data. Okay, once more, here we do get a reasonable argument why we would use the test command after using stata in one of these regression analyses. Here I left out R1 once more, so again, same thing in the regression table. Now you could argue that I can now not see if there really is a difference between R3 here and R4. This one has a minus 0.2, this one has a plus 0.2. Might be a difference there, and it turns out, first of all, that I can test this like this. Test R3 equal to R4, and then I find not rejected, supported. So it looks like perhaps there might be a difference here between category 3 and 4, but in the end, it turns out not to be the case. Finally, another test command that is typically useful if you want to test here, did it help at all? Oh, I see I made a typo over there. Did it help at all to include the religious variable here? Because the religious variable is now creating 4 of these dummies. And if I want to know something about, okay, do all these dummies taken together help the model at all? Then there is a way to test it, but it's not this one. What I should have typed here, R2 equal R3 equal R4 equal R5. I would like to type here equal R1, that's the one that I left out, and I know R1 is 0, so I should type here equal to 0 after it. And then you get a test, a joint test. How likely is it that all these R values add something as a whole to the data, or stated differently, H0 would be all these coefficients are 0. If that would be the case, how likely would it be to get the data that we have? And in this case, you'll see that, well, this is actually supported, suggesting that indeed these religion categories do not add anything to the prediction of how many perfect violations that you create. Let's see, I have on a separate slide the do file that I used, just so that you have it as well. And the only thing that I have left is that I need to introduce a little bit of the wiki data. The wiki data starts from, let's say, the relatively straightforward ones, in the sense that they stay quite close to what I talked about. And one of the later ones is this one, where we have to predict the number of airport passengers at the terminal. So you have for each and every time of the day how many passengers show up at the terminal somewhere. This is what the data looks like. So here you have a day, 1, 1, 1, 1, 1, all the same day. The hour, 6 o'clock in the morning, also 6 o'clock, 6:30, 6:45, all of the time of the day from 6:30 until somewhere in the evening. How many passengers are there? 1, 2, 4, none, and so on. The day of the week and a couple of other variables to predict. And what you see here in the data is something like this. This is a plot of the number of passengers over the day. If we want to predict this with time, I'm trying to predict as time progresses during a day, do I get more passengers, less passengers? If I do this with a straight line, as we've been doing now, then you get something like this, which is, well, it doesn't fit very well. You can see that. And we also see from the graph that there is something weird here. There's at 4 o'clock in the afternoon, there is a bit of a bump people there. And at 7 o'clock in the evening, there are more people there. And the aim of the exercise is to try to figure out how you can fit a graph like this, where you typically see that a straight line is not good enough, or can at least be improved upon, based on what time it is per day. This needs a little bit of more fumbling around with the data, so if you get stuck with that one, it's not so weird. So that's actually the only thing that I wanted to announce at this point. It's also, I think it's the 4th or the 5th one of the wiki, so by that time you should be good to go for the more complicated ones, but this one is slightly complicated. Okay, what's up next? Couple things. First, we need to deal with outliers. You want to control for weird stuff in your data. Outliers doesn't necessarily mean I have one person in the data who is 128 years old, so I have to somehow do something about it, because in all likelihood this is a coding error. An outlier is a case that messes up your results. So what you don't want to have is, I have a case in my data over here, if I take it out, and all the things that I thought were true are now not true anymore. You don't want that. And you have to be able to find them. The other thing, interaction effects, already alluded to very briefly, and all other kinds of transformations of variables that make the model fit better. We need to go through that as well. Multicollinearity is an issue, don't want to talk about what that is. And the bigger part, actually the bulk of the work, is in checking assumptions, the violations of assumptions, and what we can do about it. And that is heavy stuff. Okay, we have 2 more about multiple regression. The 2 more will be next week. So the bulk of the work is going to happen